Welcome to General Relativity for physics students. This is the third video series in our collection that covers the material from the textbook, which is Special Relativity, Electrodynamics, and General Relativity. We've had lectures already in Special Relativity covering the first 10 chapters of the textbook, taking us from the beginnings of special relativity through the formulation of electrodynamics. Then we turn to a lecture series on classical differential geometry, which serves as the basis for the geometry, the Riemannian geometry that we'll be using in general relativity. Okay. And I should say a couple of words about this. You can find additional information about the lecture series by going to the website Relativity Doctor. Okay, that's the website for the textbook. And it contains a great many supplementary lectures. And there's one supplementary lecture that covers the material of this video series. It's called Supplementary Lecture number 11. And here it is. Okay, it follows very closely the videos that will be showing here, and so it might be handy for you to follow along with the text in hand. In some cases, the text will clarify some of the equations that we'll throw up on the posters, and of course be easier reading. To see the equations here properly, you probably need a big screen laptop or a PC. Your phone isn't going to have the resolution to see the equations here. But if you wanted to use the phone, then bring along the supplementary lectures. You can bring them up from the website, or you can have your own copy, whichever you prefer. The table of contents of the video lecture series goes through the lectures in a very linear fashion, and you can find the table of contents with all of the names of the different lectures here, and follow along quite easily. It's a lengthy set of lecture notes, 165 pages or so, with figures, and it's really meant to help you learn the material. Naturally, of course, the book itself, chapters 11 and 12, cover the introduction to general relativity that we'll be doing here. I should say right off the bat that this is a lecture series that's aimed at undergraduates, junior and senior physics majors, and math majors. Okay, so it starts from the beginning, and it builds the subject up from there. It's probably too elementary for graduate students who are in field theory or elementary particles or astrophysics, although they're certainly encouraged to join in and take a look. Okay, now since we've done special relativity and we've done differential geometry, I'm not going to repeat that stuff. So in that sense, the lecture series is not as self-contained as the previous ones. Okay, we know all about boosts, Lorentz transformations, okay, electrodynamics. Okay, we've learned about the relativity of simultaneity, time dilation, Lorentz contraction. We've applied that to lots of problems. We've done collision problems. We know about dynamics. We know how to conserve energy and momentum in collisions. All of that's the stuff that's covered in special relativity, we've done. We've also taken a look at tensors. Okay, we wrote the equations of special relativity in 4-vector and tensor form. So we're sensitive to the fact that you want to write the equations of the theory in a way which is manifestly independent of the coordinate system that you're using. Okay, that's a primary constructive principle of general relativity, and we've seen that already. Now in general relativity, of course, we move up another level. In special relativity, we were interested in global transformations, Lorentz transformations, boosts, okay, and global rotations, okay. Now we're interested in local rotations, local chains of coordinate systems, so that everything becomes dependent upon the space-time position. Okay, well, we've studied things like that, of course, in differential geometry. But now we're going to be using the notation for relativity, and we'll be discussing it from the perspective of Riemannian geometry. We want to make clear the fact that the equations are true if they're true in any one coordinate system or any one reference system, they're true in all. And so we turn to Riemannian geometry, which makes that clearer. But we've seen the construction of the ideas behind it in differential geometry. In differential geometry, we study curvature. Okay, we studied two-dimensional surfaces embedded into Euclidean space, and we studied the curvature of curves, and we studied the curvature of surfaces. We studied the Gaussian curvature. Okay, and we understood how geodesics work, the straightest possible lines in two-dimensional differential geometry. We wrote down the equations of motion for them, the geodesic equations. We found various ways of measuring the curvature of a surface in classical differential geometry. Okay, and we proved the Gaussian theorem of Regium, the excellent theorem that shows you that the Gaussian curvature is a function that's intrinsic to the surface itself. That is, by making measurements on a surface of just angles and distances, you can decide how curved it is. You don't need to make a reference to the embedding space. And that's very significant in moving on to general relativity, where there is no embedding space, where we're going to live in 4 dimensions and have curved manifolds in there. So we rely on moving from curves and surfaces embedded in 3-dimensional Euclidean space up to 4-dimensional manifolds. We move from Gaussian geometry to Riemannian geometry, and that's what we'll cover. So let's take a look at the topics that we'll be covering. Okay, we'll start at the beginning, and we'll look at the equivalence principle, gravity, and apparent forces. Okay, we want to understand that gravity, okay, curves space-time, and that test particles in general relativity follow paths of the straightest kind, geodesics. Okay, and so we want to understand those ideas. We want to understand that there are certain kinds of simple problems in general relativity where you can make a coordinate transformation taking you from a physical situation in an accelerating reference frame to a coordinate system experiencing only gravity. The equivalence of acceleration and gravity is a primary concept in general relativity. Okay, that we have to understand. Okay, there's a great deal more to general relativity than the equivalence principle. There's curvature. Okay, the tidal forces. Okay, and the field equations of general relativity, and we'll get to them by and by. But we begin with the equivalence principle, and we'll discuss that in Lecture 1. In Lecture 2, we look at rotating relativistic reference frames as a simple example of what we're headed for. We want to look at the metric in a rotating reference frame and see that we find there apparent forces, Coriolis forces, and centrifugal forces, and want to see how they appear in the metric and in the equations of motion. Because when we turn to gravity will be understood not as a force, okay, but as the curvature of space-time. So it resembles rotating reference frames and accelerating reference frames and apparent virtual forces that you learned about in mechanics more than ordinary explicit forces. Well, we'll want to understand then what does it mean to have a curved manifold, and we'll see that tidal forces are the key to understanding that object. Okay, it's a topic that we covered when we thought about differential geometry, and here it comes again. Think about non-Euclidean geometry and local inertial frames of reference. In differential geometry, we spent a lot of time, okay, discussing the tangent space to a surface, okay, and then the properties of the surface. In general relativity, we talk about local inertial frames, analogous to tangent spaces, and then the manifold, which is curved itself, the space-time in which we live. The first example of gravitational effects, we'll look at the gravitational redshift, and we'll look at illustrations and relate it to energy conservation. So this is a familiar effect that you certainly heard about and read about, you know, where light is emitted from the surface of a star, okay, and then we observe it far away, okay, and we see that the light is redshifted. Okay, that its frequency changes depending upon the gravitational environment in which it is emitted. Oh, once we learn about the redshift, we go back to the twins again. Okay, well, we had a good resolution of the twin paradox. Okay, and here we'll come to another resolution of the twin paradox. Okay, remember we had two twins, Mary who stayed at home and Maria who took a trip. Okay, there was a slight asymmetry between the two excursions. Maria suffered for a very short period of time an acceleration that took her from an outgoing rocket to an incoming rocket, and it's that moment of acceleration that we want to understand and see that when we understand it from a perspective of general relativity, we get the same resolution of the twin paradox that we had earlier. Okay. Oh, well then we'll want to look at similarities and differences of electrodynamics and gravity. We spent a lot of time in lecture series number 1 understanding electrodynamics. Okay, now we're going to come to gravity, and it has certain similarities and certain differences, and we want to understand those so that we all understand both fields better. Okay. Once we have that understood, then we can start formulating general relativity. The first thing we'll do is to imagine a test particle in a curved manifold and look for its equation of motion. It'll be a geodesic equation, and we'll want to write it out in a general fashion that can accommodate a curved manifold of relatively arbitrary properties. Okay, and then along the way, when we're developing geodesics, we'll want to have a concept of the derivative, which is appropriate for curved spaces. Okay, now we know how to take derivatives in Euclidean space. We're all very handy at that. Differentiation with respect to x, y, or z. Double differentiation with x, y, and z. Making the Laplacian operator. Solving problems of the Poisson type. Okay, where del squared on a function is equal to a source, and we know how to invert that. And we've done problems like that in electrodynamics, and now we're getting ready to look at problems like that in curved manifolds, and we want a concept of the derivative which is geometric in character. Okay, our ordinary derivatives, partial derivatives, are attached to a particular coordinate system. We want a concept of a derivative which is free of coordinate systems, right? So that we can write down equations of motion and derivatives and such, which are geometric in character. That is, they're defined free of a coordinate system, and so they give rise to equations and equalities which are true in all coordinate systems because they express a geometric fact. Okay, so that's the challenge of writing down a covariant derivative. That's the terminology there. Okay, at that point, then we're ready for more geometry. We'll discuss the equivalence principle again from this perspective, a fancy perspective. We'll understand its strengths and its limitations. Okay, and then we'll talk about something called metric compatibility. Okay, choosing coordinate systems and writing down the metric in those coordinate systems, isolating what we can say on the basis of the equivalence principle, and then where we can find signs of curvature. Okay, Christoffel symbols are a primary bit of scaffolding we need in differential geometry. We saw them in our classical differential geometry. We'll see them more here. Okay, which are important in doing differentiation and doing equations of motion of various sorts. When we write down, for example, or perhaps we're solving a wave equation in 3 dimensions, but we're using curvilinear coordinates. Hidden in that formalism, there's Christoffel symbols, and we want to pull them out and see what they mean. We'll relate Christoffel symbols to apparent forces, and then to the force of gravity. Okay, that's where the gravity and curvature will appear in our equations, and we'll have to have due diligence and be careful about that. Get that precise. Okay, and we'll be very precise about that. We'll turn to curvature, space-time, and the Riemann tensor. The generalization of Gaussian curvature from surfaces of 2-dimensional character to manifolds in 4-dimensional space-time. We'll be ready then to formulate the Einstein field equations of gravity. Roughly speaking, the popular way of saying this is that curvature is induced by the energy-momentum tensor. Okay, you have mass or energy in some region, okay, and it curves, warps space-time, and the way space-time develops a curvature, okay, which then affects the equations of motion of test particles in that vicinity. Okay, now we want to turn to some classic exact solutions, and the first one, naturally, is to look at a spherical body, which is static, and calculate the space-time around it. That's the Schwarzschild problem and the Schwarzschild metric. Okay, and we'll do that. Okay, and then we'll find, okay, that if you can make a body with sufficient mass and sufficiently small enough, you'll create a black hole. Okay, you'll create a region of space-time from which bodies can enter, but never come back to the outside world. That's called black holes, and we want to see how they work and study their properties from several different perspectives. So we'll get the Schwarzschild metric, and then we'll do a whole bunch of problems. Okay, we'll want to understand what happens when you shoot light rays out of the vicinity of a black hole, maybe into a black hole. If you take a particle and drop it into a black hole, how long does it take for it to go past the horizon and get swallowed up by the singularity at the origin? Okay, so we'll do problems like that, orbits in the Schwarzschild metric. Okay, and we'll do enough here to illustrate the ideas, and there's lots more that, of course, that one studies in these problems in further courses. And then we're ready to look at relativistic tidal forces. Our first introduction to tidal forces will be very intuitive, based on Newtonian concepts, but we'll see that it generalizes to gravity, and then it will be ready at this point to get a relativistic description of tidal forces and relate it to curvature and related to geodesic deviation. So remember from our discussion of classical differential geometry that one of the ways of seeing if a surface is curved was to look at two nearby geodesic paths and see how quickly or how slowly those paths tend to come together or spread apart. That's called a geodesic deviation. Okay, we derived the equation for the geodesic deviation in differential geometry. It was called the Jacobi equation, and we studied it in various cases. Illustrated it on the sphere, illustrated it for hyperbolic geometries, and here we'll express it again in the language of Riemannian geometry, and then use it in various applications. We'll use it in the application of the discovery of gravitational waves. Okay. Well, we all know in electrodynamics that you shake a charge, okay, accelerate it, and it'll give rise to radiation. Similarly, in gravity, if you accelerate masses, that acceleration will give rise to gravity waves. The most common electrodynamic waves that are generated from checking a charge are dipole radiation that we've taken a look at in the first lecture series, and hopefully you've studied in your electrodynamics courses. Well, in gravity, things are different. Gravity is a tensor, and so gravity waves are characterized by quadrupole moments, not dipole moments, and we'll want to understand that, parameterize it, get used to it. Find the similarities between photons and gravitons, between electromagnetic waves and gravitational waves on the other hand. There's some similarities, there are some differences, and we want to understand those in intuitive fashion, but also we want to understand the formalism of the differences and similarities between them. That's what we'll study when we look at the contrasting special and general relativity. And then we'll discuss some interesting timely problems. The cosmological constant, a few words about dark energy, and the accelerating universe. I'm not doing cosmology in this course, okay, we're just doing basic general relativity, okay, but this is just a bit of a teaser to something that you might study more of, and it presents challenges to the field which are, to this date, unsettled. Okay. Now, we don't end at this point. We end with what's called special topics. These are just topics which could be put into the first half of the lecture series. They're just in the second half of the lecture series because of just how things went. You know, if we had to do it over again, maybe I would do rotating stars and emphasize them more than the Schwarzschild metric, which is appropriate to a non-rotating spherical mass. So when we get here to special topics, okay, we'll just be continuing along in the same style as elsewhere. Some of these topics are rather self-contained, and others are just part of the course, moving forward in a continuous fashion. So special topics. We'll look at rotating stars, gravitomagnetism, and the Kerr metric. So the first and simplest exact solution of the formulas of general relativity is that of Schwarzschild for a mass which is symmetric and static. Then early in the 1960s, okay, Kerr came along and did the problem for rotating a star. Okay, so it's a problem with axis symmetry, not spherical symmetry, a more challenging problem indeed. And he wrote down the exact metric for that sort of environment. And this was a great thing for the field, because all of a sudden you had an exact metric for a very important astrophysical object, a rotating star, and perhaps if that star has gone through its evolution and it was initially massive enough, a rotating black hole. Rotating stars, of course, are common in the cosmos. Non-rotating stars that might develop into a Schwarzschild metric late in their evolution are very uncommon. Most stars rotate, okay, so these are the objects. These are the black holes that we study. These are the objects with accretion disks, okay, with jets and all of that wonderful astrophysical phenomena. So if we have an exact metric for it, we can really make progress on it and really get in there and understand its interesting phenomena. And one of the interesting phenomena is, in this case, we have gravitomagnetism. Okay, we know from our studies of special relativity, okay, that special relativity itself outlaws ordinary static Newtonian style forces. That forces necessarily are velocity dependent in special relativity, because that just comes in from the requirement of covariance. That is, if you have an ordinary static force like 1 over r squared of static charges attracting one another, well, then if you boost that force to another frame, you find that in addition to the forces of electric character, you have forces of magnetic character. There's nothing to do with electromagnetism. Okay, it's nothing to do with a particular field. It's a property of special relativity and the transformation law of special relativity, that velocity-dependent forces are necessary. Okay, and so they're going to be necessary in general relativity also, and we'll find a form of magnetism. We want to distinguish it from electrodynamic style magnetism, so we call it gravitomagnetism. Okay, and we'll see it coming. We'll get at it from several different directions. I'll do a class of problems where the relativistic gravitational fields are weak, okay, and then I can attack it as a problem in special relativity. And then I'll turn to problems like the curve metric, where gravity effects are strong, and then we'll have to learn to read it out of the Kerr's metric, and we'll be doing that. Okay. Okay, along the way, we want to increase our bag of tricks. We want to understand symmetries and conservation laws. We will have seen this, symmetries and conservation laws, in our discussion of Schwarzschild metric, and we want to systematize some of that here. Okay. Then we'll turn to accelerating clocks and the twins again. Okay. One of the things I've noticed is that there's a lot of confusion out there about what are the limits of the types of problems you can do in special relativity. Okay, a lot of the textbooks in special relativity always look at problems with a fixed constant velocities. Okay, well, special relativity does focus on constant velocities, okay, because it's looking for inertial reference frames. Okay, and we learned that if you have an inertial reference frame, you can make a whole family of additional inertial reference frames by doing boosts, making Lorentz transformations of fixed velocities. So you talk about fixed velocities a lot. That means that a lot of books just lose sight of the fact that they're also discussing equations of motion. And in equations of motion, you have forces pushing around particles, and those particles experience acceleration. They're experiencing changing acceleration called jerks. They experience arbitrary motion. And that is the subject of special relativity. Acceleration is the subject of special relativity. How does that differ from general relativity? General relativity is the theory of gravity and curved space-time. In special relativity, you study acceleration, but you do so in Minkowski space. Okay, you don't have masses, large masses around. You have an inertial reference frame, and within that inertial reference frame, you have accelerating particles. Well, you might have accelerating clocks. So let's see how accelerating clocks work. Let's put accelerating clocks, okay, on a twin. Okay, give the twin some charge so I can accelerate her in a cyclotron. Okay, and see and measure her proper time with respect to the time measured in a lab, in a reference. So compare the clocks between the twin who's accelerating, okay, and her other twin who's sitting in a lounge chair in an inertial reference frame. Okay, that's a useful thing to do. We'll do that, and we'll find another resolution of twin paradoxes there, and generate some interesting big effects. Well, once we're in that direction, we might as well go all the way and make an accelerating reference frame and do a subject called the Rindler wedge, or Rindler space. So Rindler space is just to view Minkowski space from the perspective of a very large rocket ship, okay? And the large rocket ship provides a coordinate system for a fraction of the Minkowski space that you're choosing to accelerate through. Okay. Well, you know, if you take ordinary Cartesian space, then you might parameterize it with x, y, and z, but you might parameterize it with spherical coordinates, r, theta, and phi. But if you give me a Minkowski space, I might want to look at it from the perspective of one inertial system or another inertial system, but I might want to look at it from the perspective of a rotating turntable. That's a non-inertial reference frame. Rindler wants to look at it from the perspective of accelerating reference frames. Okay, and let's do that, and you know, and see a lot of the effects of acceleration there. In particular, we'll study the Rindler wedge, okay, which is a kinematic effect that has a horizon. So we'll have a little model of black holes. And along the way, we'll want to look at geodesic precession again. Okay, and that'll cover the course. And so next time, why don't we begin with lecture 1 and look at the equivalence principle, gravity and apparent forces. Okay, so see you then.